Here is an engaging, STEM-focused explanation of quadratic equations designed to motivate high school students. The hidden code of the physical world. Why quadratic equations matter. Imagine you are watching a slow-motion replay of a basketball player launching a game-winning three-pointer. As the ball leaves their fingertips, it doesn't travel in a straight line. It arcs gracefully, reaches a peak, and then curves downward into the net. That perfect arc? It's not just luck, it is a parabola, the geometric shape defined by a quadratic equation. In the world of STEM, science, technology, engineering, and mathematics, quadratic equations, $x2 plus bx plus c equals $0, are not just abstract algebra problems, they are the mathematical source code that governs gravity, acceleration, and structural design. To truly understand their power, visualize a projectile motion animation. Whether it is a soccer ball kicked into the air, a water fountain stream, or a rocket launching into space, the trajectory follows a quadratic path. Here, the math directly maps to reality. The $x axis represents horizontal distance or time, while the $y axis represents height. The most critical point on this curve is the vertex, the very top of the arch. For a NASA engineer, calculating the vertex isn't just homework, it's how they determine the maximum altitude of a spacecraft. Similarly, the roots, or $x-intercepts of the equation tell us exactly where and when the object will hit the ground. By solving for $x, you aren't just finding a number, you are predicting the future location of a falling object. Now shift your focus to civil engineering. Picture the Golden Gate Bridge. The massive main cables that hold up the roadway form a perfect downward opening parabola. Engineers use quadratic equations to model this curve because it is the most efficient shape for distributing the immense tension and weight of the bridge. If the curve were calculated incorrectly, the structural integrity would be compromised. In this context, the coefficient $a in the equation determines the steepness or width of the curve. A wide, shallow cable has a small $a value, while a steep arch has a larger one. This is a real-life application of transformations you learn in class. Finally, consider the technology in your pocket and home. Satellite dishes and the reflectors inside your car's headlights are 3D parabolas, called paraboloids. They rely on a unique property of quadratics. Any signal or light ray entering the dish parallel to its axis will bounce off the curved surface and hit a single precise point called the focus. This is why satellite dishes are curved, to collect weak signals from space and concentrate them onto the receiver. Without the quadratic geometry ensuring that every signal reflects to the exact same spot, we wouldn't have satellite TV, GPS, or focus beams of light for driving at night. In summary, quadratic equations are the language of optimization and motion. They allow us to calculate the safest stopping distance for a car, which increases quadratically with speed, not linearly, design stronger structures, and predict trajectories with precision. When you solve for $x, you are decoding the rules that keep bridges standing and satellites communicating.